All right, everyone. Today is our first video for section 5.4, and so in this section we're going to be dealing with optimization problems. And what we've done is kind of chunk them up by three different groups of problems. So our first group is going to be boxes, numbers, and fences. And these will kind of be the stock problems you see when we do optimization. So for our first one, this is very similar. It's actually the exact scenario that we modeled today in class with our pieces of paper and folding up those boxes. So we're making an open top box by taking a 54 by 30 centimeter sheet of paper, cutting out squares out of the corner, and then bending them up to make the sides of our box. So the question here is, how large should the squares be to make the box hold as much as possible? So what we need to recognize here is that what we're trying to maximize is the volume, because I'm talking about how much the box can hold. So our goal here is to maximize the volume. Okay, and then we'll answer the question, once we've found the dimension that will maximize it, what is the actual volume? So now, I know I'm going to be dealing with volume, so I'm going to need an equation for volume. But before I start coming up with that equation, I'm going to go ahead and draw a picture that kind of represents what's happening here. Because a lot of times that's going to help us kind of organize our work and figure out what we need to do. So there's my piece of paper, and I know I'm cutting out squares out of the corner. And the dimensions of those squares, they have side length x. So now, I also know that the width of my paper, let's say, is this 30 centimeters. So if this whole width is 30 centimeters, I know after I've cut out those two squares, what I'm going to have is 30 minus 2x. And then for the height, I have a similar thing. I have 54 centimeters, but I'm cutting out those two x's, so I have 54 minus 2x. So now we're ready to come up with our equation for volume. Oh, one thing I do want to talk about is our limitations on the value for x. So looking at these expressions, right, I know that this resulting width, after I cut out the two squares, has to be greater than 0. Right? So that tells me that my x, right, it's going to be, right, I know I'm cutting out squares that are greater than 0, but for the remaining paper to be more than 0 as well, the most I can cut out, that's going to have to be less than 15. Because if I cut out even 15 centimeters, then this width of paper is going to be gone and I won't have anything to make my box with. So ultimately, I'm looking for a value of x that's somewhere between 0 and 15. So let's go ahead and put together that equation. I know my volume is length times width times height. So let's plug in the values we have. We know we have 30 minus 2x times our 54 minus 2x. And then the height of that box when we fold it up is going to be x. So I'm going to expand this out so it's easier when we come to differentiating. So 30 times 54, I get 1,620 minus, let's see, 108x minus 60x, and then plus 4x squared, and that's all going to be multiplied by x. So I'm going to take my highest degree first. So I'm going to have 4x cubed. Now negative 108 minus 60 is negative 168. So I have minus 168x squared. And then plus 1,620 times x. So that's my equation for volume. Now, throughout this whole chapter, what we found out is that when we want to find the maximum or minimum value of a function, what we need to do is take its derivative and set it equal to 0. And that's exactly what we're going to do here. To optimize or maximize our volume, I need to find the derivative of my volume. I'm going to set it equal to 0 and then solve for the value of x. So this is a nice, easy derivative. I have 12x squared minus, let's see, minus 336x plus 1,620, and we're going to set that equal to 0. Now, I happen to know that this is not factorable, so we're going to use our graphing calculator to help us figure out the value of x pretty quickly here. So, since I want to know the zero of my derivative, I'm just going to type in that function. Whoops, 1,620. I'm going to graph it, and I'm going to use my calculator to help me find that zero. So it looks like it's going to be 2, 3, 4, 5, somewhere between 6 and 7. So I'm going to go to second calc. I'm going to use my 0 here. And now I've got to get my left and right bound. So I'm going to keep scrolling until my left bound kind of comes into view here. Okay, there's my cursor there. So I'm going to hit enter for my left bound. Then if I go one over, I've dropped below the y-axis, so that's fine. Hit enter for my right bound, hit enter again, and it gives me a 0. So 6.1897503. We're going to go to the thousandth, so that's going to give us about 6.190. So now I know that I want the squares to be 6.190 inches squared. Or not inches squared, that would be the area, but the dimension should be side lengths of 6.190. So let's say that. And we're going to make sure we include our units because they were included with the problem. So there's the first part of the question. Now, it says, what is the resulting maximum volume? So to get the volume, we're just going to plug into our volume equation, and we're going to find the volume when x is 6.190. And again, I'm going to use my calculator to find that. So I'm going to plug into this expanded here. So let's see, I've got 4 times 6.190. Whoops. Cubed minus 168 times 6.190 squared, and then plus 1,620 to 6.190. And so we get the volume is approximately 4,539.402 centimeters, and since it's volume, that's going to be cubed. So that's our first type of problem, is a box problem. Now, the next problem we're going to look at is number 2. So it says find two numbers whose sum is 16 and whose product is as large as possible and as small as possible. So the first thing I'm going to look for here is I know I'm trying to maximize or minimize the product. So I'm going to need an equation for that. So when I look here, I notice I have it says find two numbers whose sum is 16. So I'm going to call my two numbers x and y. So if their sum is 16, I know I have an equation that's x plus y equals 16. But we said we're trying to maximize or minimize their product. Well, the product, and we'll call that P for product, is just x times y. Now, I'm a little bit stuck here because I know I want to differentiate and solve for, differentiate, set it equals to 0, and solve for x, but I have two variables here. And so that's where this equation is going to come in handy. I want my product just in terms of x. But I can rearrange this equation to get y in terms of x. So if I rearrange it, I know y equals 16 minus x. And now I can just plug in this value of y into my product equation. So now my product of x is x times 16 minus x, or 16x minus x squared. So now I've got an equation that's just in terms of x, so now it's easy to differentiate and solve. So I get p prime of x equals 16 minus 2x, which is equal to 0. And so we could see that x is equal to 8. So now I've got one of my values, but I need to decide whether that's a maximum value or a minimum. So I'm going to do a quick check. I'm going to do our number line like we're used to doing. And so I know for my function I'm going from negative infinity to infinity. And x equals 8 is my critical point. So if I plug in something less than 8 into my derivative, say I plug in 0, that's going to give me 16, which is positive. If I plug in, let's say 10, I'm going to get a negative number. So I know that I'm going to be maximizing my product when x equals 8. And there's no other extreme value. So if I look at the whole domain of this function, I'm going to maximize product when x is equal to 8. And now if I go back to my equation, if I plug in 8 for x, I get that y is also equal to 8. So unless I restrict that domain, I'm only going to get a maximum product. I'm not going to get a minimum product. I want to look over here, though, just quickly. Let's say I restricted this problem now, and let's say I said find two whole numbers. Okay, so let's say I changed a little bit and I said find two whole numbers, still whose sum is 16 and whose product is as large as possible or as small as possible. Nothing changes about my equations here. But now if I'm talking about whole numbers, now my domain is x greater than or equal to 0. So when I test my points here, now I also need to test my endpoints. So now I have an endpoint of 0, a critical value of 8. Whoops, that should be 8. And this will be infinity. Now, if I test a value between 0 and 8, again, I'm going back to this derivative. Let's say I plug in 1. I'm still going to have a positive. And this is still going to be negative. But now, since I was increasing from 0 to 8, I have a minimum at x equals 0. So now I can minimize my product when x equals 0. If x equals 0, that means y is 16. So I just wanted to show that to talk about how domain can impact that problem. All right, our last one, number 3, another very typical problem. We have a rancher who wants to construct a rectangular corral using 200 feet of fencing, and he's going to build it adjacent to a barn. So really what's happening is, let's say here's my barn, one of the walls of my barn, and I'm just building the corral off of that barn. So the question asks us what dimensions the rancher should use to construct the corral so that it will enclose the largest possible area. So again here, this is telling me that what I want to do is maximize my area. So I'm going to assign some variables here. I'm going to call this x and this y. So I know the farmer has, or the rancher has, 200 feet of fencing. So that means to do this fence, I would need actually 2x and then plus y. That's got to be 200. And my area of that enclosure is x times y. But again, I want to get an area function that's just in terms of x. So I'm going to rewrite this equation. I'm going to isolate y, so that's 200 minus 2x. And again, I'm going to go back and substitute here where I have y. So my area in terms of x is x times 200 minus 2x. Or just 200x minus 2x squared. So now I can differentiate. A prime of x is 200 minus 4x. I'm going to set that equal to 0. So that's going to give me an x equal to 50. So now I've got one of my dimensions, and that's what they're asking for. What dimensions should I use, or should that rancher use? So if x equals 50, well, we said here that y equals 200 minus 2 times x, which is 50. So that's going to give us 100 for y. So now my dimensions are 50 feet by 100 feet. And I can go back and quickly check to see that that makes sense. We said that we were going to use 200 feet of fencing. So if x is 50, and this is 50, and then this is 100, if I add those up quickly, I do get 200 feet. So that's our first type of problem that you'll be getting lots of practice with tomorrow in class.